How you doing today? We're in chapter two of Water and Wastewater Laboratory Techniques, this book. And we're going to talk about analytical and top balances. Um, it's the book says one of the first analytical instruments encountered by laboratory technicians is the balance. A balance is a device used to determine mass, specifically designed to work on uh, the surface of the earth. So I know all of you guys are familiar with scales that you weigh yourself with. Um, in the water and wastewater technique lab, we're going to use a laboratory scale. Concept is the same. We're measuring mass, but the precision is a little greater. So why do you use a scale? Well, a lot of our results from our laboratory tests are results that we have derived from adding a reagent or pipetting a certain volume into some sort of flask and then either drying that flask or some other step that we've done with it and then weighing it out to make sure that we get the solids concentration or the specific mass of that liquid or sample that we are um, using. So, types of balances. It talks about the archaic balance that's at the Department of Justice in Washington D.C. It consists of a balance head held on a nice edge with a pan attached to it. But we've went a long way from those days, and we are now more into more accurate um, top loading balances and analytical balances. So top loading balances are used in the laboratory to weigh out reagents for preparation of solution and for this sample dispensing with a sensitivity down to 10 mmg, depending on the maximum capacity. Most balances have incorporated electronics to some degree to speed up those determinations. The electronics allow automatic zeroing, calibration check, and simple tare determinations. Some models will send the determined weights directly to a computer system for automated data logging. So a top loading balance you can see in figure 2.2, they're down to 2 mg. An analytical balance has that same concept, except it's more sensitive, and we can go down to um, a lower a lower weight, more precise weight at those smaller numbers. And you can see there's a dust shield there, a dust shield and wind shield. It's so precise that we want to keep dust off the plate. Even a little bit of dust will, make the balance out of proper calibration. Um, any type of wind, obviously, wind can, just move that balance ever so slightly to change your recorded weights. Balances are sensitive to gravity, humidity, temperature, static electricity, dust, dirt, vibrations, and air current. Um, most balances have a bullseye spirit level in the back and the feet adjust. So if you look at that balance in the back, there's feet that adjust up and down, kind of like your washer and dryer do to get it level. You want your balance in a room where there's not a lot of wind, a lot of dust, a lot of vibration. Ours is set on a marble top because it won't move. Um, we want to protect it from all that. We keep our lab at 70 degrees, so the temperature uh, is um, is consistent. Laboratories in areas with high humidity find it difficult to attain stable reading. Dust and dirt. are the banes of balances because they limit the ease of the movement of the mechanical parts. Um, so, we just want to make sure that we're using the draft shields, make sure that we don't have like a air conditioning vent right over the balance. All those things are important when we talk about balances in the lab. The only person who can calibrate a balance is a balance service technician. Now we calibrate it once a day, but they come in, or we check the calibration once a day, I should say. So every day we turn the analytical balance on. We do a self adjustment, and then we check that with one of our registered weights, and then we record that on one of our lab sheets. But once a year, we'll have someone come in using class one weights, um, and a certified technician will come in and verify our weights. And those certification materials are then recorded in the lab, and we keep those records so that we can um, give those to the regulatory agency. Um, when we talk about modern electronic balances, it has keypads and a digital digital display for faster operation. Let's talk about tare and zero. So zero is setting the balance to read exactly zero when the pan is empty. Tare is the weight of the sample container. Because if we had this sample container, obviously there's water in it. So tare would be the weight of the the weight of the empty sample container, because we want to know just how much the water is in there. So the tare weight of the container should be recorded in the balance logbook or on the sample analysis bin sheet. This weight is subtracted from the final weight of the sample in the container. Many electronic balances can perform the subtraction automatically by the digital readout to zero when the tare function is pressed. Now, this is important. Uh, then, when the sample plus container is read, the indicated value is of that sample alone. This is poor analytical practice for several reasons. This gives the illusion that for a balance with a maximum range of 200 grams, the whole range is available for the sample determination when the tare is set to zero. In reality, the full 200 grams is available only for the sample plus the container when the empty pan is set at zero. Second, there is always an elapse of time between the determination of the weight of the sample and the determination of the final weight. During this lapse of time, another technician could have used the balance and changed the tare weight, making the final weight meaningless. Third, there is no written record of the chain of calculations, which begin with the initial sample amount tested in the ends final parameter concentration in the sample. Fourth, the ability of the balance to read exactly zero with an empty pan it's itself a calibration check of the balance. The inability of the balance to read zero on an empty pan is an indication that the service technician should be called. So, if you're not tearing correctly, when you take this glass off of there and there's nothing on the weight, that scale should read zero. But we want to be able to tear out this glass so that we can just measure the weight of the water. We want to use those tare functions. You can see pans. Those are pans that we use for weighing. One thing I'll mention with those pans is that we will use tweezers to touch those pans because the oils off your hands actually can change the weight of those pans. And so when we're weighing out um, stuff, we want to use tweezers. Several accessories made working with analytic easier. The first is a brush for removing small spills of reagent samples in the balance. So, having a brush that's, used for that scale to brush it off because you do spill some reagent on it when it doesn't do zero. is uh, is is important. Uh, the balance is easy to use. This is on page 24. First, turn the balance on, let it warm up, and make sure the doors of the draft shield are closed every time a weight is determined. Check to make sure that the bubble in the bullseye indicator is exactly centered in the circle. The second step is to depress the tare button with the pan empty. It should stabilize 0. Record the reading, and then select one of the calibration weights from the set and carefully place it on the balance using forceps. A weight about the same mass as the intended weighings is most representative. After the reading stabilized, record the exact weight on the bench sheet or the balance. If the recorded weight is in the tolerance of the calibration weight, weigh and record each of the sample filters. Pick up the filter with the forceps, place on a balance plan, and close the draft shield. That's the basics for using a balance in a laboratory. If you have any questions, you feel free to message me. Thank you.